Hi, good morning, good afternoon, depending on where you are today. I'm very pleased to introduce Robert Abraham, VP of Engineering at Adjust. Based in Berlin, they're one of Aerospike's biggest European customers. He's going to be talking to us today about user attribution at scale. With over 500 billion objects in their database, this is a subject he's very well qualified to discuss. So, thank you, Robert, and over to you.
Thank you, Ken, and hello and welcome to my talk today. So, this story starts in 2012, and this is the story how we scaled our attribution engine from a few requests per minute to over 700,000 requests per second. But first things first, who is Adjust? So Adjust is a global app marketing analytics platform committed to ensuring the highest privacy and performance standards. Adjust solutions include attribution, measurement, fraud prevention, cybersecurity, as well as automation tools. But the company's mission is to make mobile marketing simpler, smarter, and more secure for the more than 50,000 apps we are working with. To ensure full compliance and control of our data, we run our infrastructure on bare metal servers. This allows us to use the full potential of our hardware, since we control everything from the network to the machines. Having this level of control over our own infrastructure is a powerful tool to discover bottlenecks and problems so that we are able to act in time and accordingly. So now, who am I? As Ken already pointed out, I'm Robert Abraham and I'm the VP of Engineering at Adjust. And as you saw, Adjust was founded in April 2012, and I joined the company in October 2012 as the head of VP operations, IT operations, and one of the first employees. But actually, I was part of the founding process from the beginning, and I first consulted with the founders, and then we decided on how we want to set up the infrastructure, and later then I joined as an employee. So the main task of my team and me was to design a modular system, and this is more or less still in use today. Obviously, we updated and added new components where it made sense. From April 2012 until today, we scaled our infrastructure from a little over 10 servers to more than 1,000 servers that are distributed in 4 data centers around the world. And as I mentioned, at the same time, we scaled our infrastructure to deal with like a little less than 40 requests per minute to more than 750,000 requests per second. And today we want to take a look at a few of the challenges that we faced on the way. So the first question is, what is mobile attribution? On a very high level, mobile attribution is the science of matching 2 data points, such as clicks or impressions with installs, or ad spend to user engagements. Attribution then helps the marketer to understand what happens when the user interacts with mobile ads. A successful mobile app attribution shows the complete journey of a converted user. This allows the marketer to see if a user reacts upon seeing an advertisement, whether the advertisement causes the user to install, and how the user interacts with the app after installation. This does not only help the marketer to understand individual users, but also to identify relevant cohorts that do or do not respond to their creatives. Now, attribution is central to everything that Adjust does and the foundation of all of our products. Is it measurement, protection, or automation? And this is how it works. So the app acts as an advertiser. The advertiser buys traffic on an ad network, and this will start serving ads to their users. The ad hopefully creates interest in the users, and eventually a user clicks on the ad. The ad redirects the user to the App Store, where the user downloads the app. Now it just sits in between the ad and the App Store, and our SDK is integrated in the app of the advertiser. That means that we are able to verify that the ad was served by the ad network that eventually triggered the install. Now, this is important because that means that the ad network cannot just tell the advertiser that they actually served the ad, but there's an actual way to prove that this happened. So, and if there are more than one ad network is involved, this gets even more complicated. So that's why Adjust is there to help act as a trusted partner and user, and to verify that conversions actually happened, and to verify that in an objective way. Now let's actually talk about the tech and let's talk about our setup. So as we already figured out, there's an SDK. And our infrastructure is designed to be as modular as possible, and the data flow is the following. So the SDK collects the data in the app and sends it to our tracking server. The tracking server creates or updates the device data in the device data store. And then the tracking server will hand over the incoming data point to a queue, and all subsequent processing is done asynchronously. So we will then do the fraud detection, the attribution, aggregation, and sending out postbacks. This is obviously a very high-level illustration of what happens. There are a lot of services and components involved, and some of the parts of our stack are written by Adjust and maintained by Adjust, and some are not. And the device data store is one of these things that are not written and maintained by Adjust. While the basic design is more or less the same since 2012, most of the individual parts were altered or replaced. One of the biggest changes in our stack was the migration of the device data store from Redis to Aerospike. And today I want to guide you through that journey. In fact, we did not only change that part once, but several times. So the data stored in our device data store is a map from a hashed device identifier to the device data. And the device data is, for example, last session time, last country, and so on. Naturally, we choose a key value store for this use case. The initial list of requirements were a fast response time, high throughput, enough storage capacity for the expected amount of devices, and of course, fault tolerance. So in early 2012, we decided to use Redis as it satisfied all of our requirements. Redis benchmark showed that the subset of commands we wanted to use were all served in sub-milliseconds, and we could easily respond to over 40,000 requests per second. In regards to storage, we would have been able to store the device data of a large portion of all the mobile devices that existed back then on a single server. And we were only using a cheap Hetzner machine that had 32 gigabytes of RAM and 2 terabytes of HDD storage. For simplicity, we settled with a simple and easy to maintain primary replica setup. And when we onboarded our first customers, we operated well within the specifications and we were vastly over-provisioned. Now, between 2013 and 2014, we had our first very strong growing phase. A few requests per second became a couple hundred requests per second. We onboarded more and more customers and we saw more and more devices. On top of that, we developed new features and added more data to Redis. So the payload of our data grew bigger and bigger. So our first bottleneck that we approached was the storage capacity. And as you all know, Redis is an in-memory database, so all the data has to stay in memory. In order to deal with that, we thought, why not simply migrate to bigger machines? So basically, there was no real migration per se. We just added, or we just migrated to bigger nodes. The strategy for that was relatively simple. We added a replica with more storage, and then we failed over to that. Our hoster back then was able to provide us with machines with up to 384 gigabytes of RAM. So we were able to scale vertically for basically some time. However, at some point, even this was not enough anymore, and we needed to find a way to scale even further. And we had two main problems. The first one was the limitations provided by Redis. Redis is single-threaded, and hence it does not really benefit from modern multi-core CPUs. And the other problem we had, that we could only put so much memory in one machine. So we also hit the physical limits of single servers. So we needed to develop a strategy to actually scale Redis horizontally. And we came up with this. So fortunately, Redis evolved with us, and Redis Sentinel became stable. Sentinel is part of the Redis distribution and can monitor primary and replicas and do automated failovers if necessary. It also allows users to run custom scripts after the failover was performed. So that was very handy here. Another software that reached maturity at this time was Nutcracker from Twitter, which was later renamed to 2M Proxy. As you know, 2M Proxy is a load balancer that you can strap in front of a large number of Redis servers and load balance a request. So now we decided to take Sentinel, 2M proxy, and Redis and glue them all together. Now each server was able to run several instances of Redis. This enabled us to benefit from multi-core servers, even though Redis is a single-threaded application. Also, we were able to distribute these Redis instances over as many servers as we wanted. Now, all primary replica pairs were registered at Sentinel. Sentinel then made sure that there's always a consensus and that there's a possibility to failover, because Redis Sentinel itself is clustered software, so it implemented the consensus algorithm. And if you have enough Sentinel nodes up and they notice that a node goes down, then they will get a quorum and then they will perform a failover. Then a new or former replica gets promoted. We have a new primary, everything reasons, and then you have again like a consistent cluster. All writes and reads to the cluster go through 2M proxy. So 2M proxy is also also needs to be configured by Sentinel. And that means if a failover event happens, Sentinel is responsible to A, do the failover of Redis, and B, reconfigure 2M proxy. Now, each client also had their own 2M proxy instance running and their own Sentinel running. So even if a client goes down, this context, the client was a backend server, we didn't lose any availability. Now, the result was a Redis cluster that could be scaled horizontally. It did not only fulfill our initial requirements, but we were also able to add machines when we needed them, and we were able to overcome the limitations of single Redis instances. Basically, all problems we had were solved, and we felt like this. The new system was working very well in the beginning. The scaling mechanism was similar like before, like adding a new replica and then failover. But now the failover was to a different server instead of just a bigger instance. And then we resynced the primary from the primary and everything was shiny. As you probably already guessed, this is not the end of the story, because that's why we are here today. So this setup is really complex. Like you saw, there are lots of lines, lots of connections, lots of moving parts. And soon we ran into the first problems with that. And the biggest problem we had at the beginning was the automation. So Sentinel configures 2M proxy and Sentinel maintains its own state. Like you cannot just export the state from Sentinel. It's like in itself, in memory, in the config, it's all written down. And the config is dynamic. So you cannot just deploy the configuration for your cluster via automation. And every time you add new servers, you need to do some manual work. And manual work is error prone. So this became more and more a problem the more servers we added. And we never were able to really work around that. But despite that, it was still smooth sailing for us. But then we ran into the next problems. In early 2014, we were experiencing weird latency spikes. When the application tried to talk to the Redis cluster, some answers started to take almost a second instead of a few milliseconds. Redis Slowlog itself reported no issues, all queries were as fast as expected, and the issue was not easily reproducible. So we did some debugging and correlated Redis logs with application logs, and then we found the root issue. Redis uses AOF files for persistence, and AOF files are some kind of write-ahead log. Once these files exceed a certain size, they get rewritten and compacted. However, this rewrite happens after a fork, and this call stalls the application. So our Redis instances had become so big that even a fork became very expensive. And this means that the complete application was stalled for sometimes over a second. We were kind of able to mitigate that by manually triggering these rewrites when we were off-peak. Then another problem we encountered was that our average response time was suddenly going up. In theory, Redis guarantees constant complexity for get and set operations, and the size of each Redis instance should have no effect on the response time. And in synthetic benchmarks on our staging system, we also saw that Redis should be able to answer a lot faster. And again, we debugged search logs, compared stuff, and at some point we found out that the AOF logs were again the bottleneck. So we used in the beginning HDDs for the storage of the AOF files, because we just didn't anticipate that in an in-memory database, I/O bandwidth could become a problem. But unfortunately, it was a problem. So we had two options to mitigate that: either disabling fsync on AOF writes or upgrading all the servers to SSDs. And well, eventually, all Redis servers were upgraded to SSDs. This made these machines even more expensive. Also, on top of that, our dataset grew, and we had to add more and more nodes. And due to how the system works, adding a node means a failover from one machine to another machine. But the sheer size of the single instances makes this also more painful. In the beginning, a complete failover resync cycle took less than a minute. At the end of 2014, it took almost an hour. Also, due to how the reconfiguration works, which means that it needs to restart the local client, a failover always meant an actual short service interruption and a backlog into the pipeline. Last but not least, the infrastructure cost became a huge burden. Within 1.5 years, we grew from 1 to over 40 servers, and we had to add 2 new machines every 2 weeks. So the servers needed now the maximum amount of RAM and the maximum amount of SSDs, so they became quite pricey, which basically made us feel like this. So in the last days of the cluster, we were operating well outside the comfort zone of Redis and also well outside of the comfort zone of the engineering team. So this were how we and the cluster felt. Now, I don't know about how you feel about migrating from one software to another, but we decided that we have to let go at this point. Not everything we learned was in vain. We learned a lot about our systems as well as about our applications that we wrote. Like, we faced issues with the Linux kernel, we faced issues with NUMA domains, disk and bandwidth saturation. And at least we learned how and what we should monitor and where we should look. But still, we needed to find a successor for our Redis cluster. So we went ahead and we evaluated several options. But in the end, they all had the same 2 issues. Either they work pretty well in normal operation, but as soon as you brutally removed a node or added another node or simulate other problems like network interruptions, the performance just plummeted. Or they were equally complex like our Redis setup, and they required a lot of maintenance and care. And we wanted to solve both of these problems. So our problem was, our solution was actually to migrate to Aerospike. So when it comes to our use case, Aerospike acts very much like we wanted Redis to behave. It has clustering built in, and you can seamlessly add and remove servers from your cluster. So only the lookup index, which in our case is the hash of device identifiers, is kept in memory, and the data itself is stored on SSDs. This means that the majority of data can be kept on a storage that costs like 1/10. And as described earlier, we needed fast storage anyway. We were able to reduce the node count from 40 to 6. This means we were able to cut our infrastructure costs by almost 85%. And we also needed to maintain it a lot less. This means we had more resources available to build new features and products. And even with our growing data sets, the latency of the operations were stable. As a bonus, Aerospike had a lot nicer interface for the internal metrics, and it also allowed us to monitor the stats more efficiently. So in 2015, which was when we finalized our migration to Aerospike, this is basically, these are the metrics that we had. So even after switching to Aerospike, the amount of data we had still continued to grow, and we added more and more servers to the cluster. But this is how the first iteration of our setup looked like. And as you can see, the TPS was moderate and the amount of data was not too big. And at this point, we were still only in one data center. But it was working perfectly fine for us and was great. Obviously, such a big migration does not come without any problems. I want to highlight that all of these issues came up somewhere between 2015 and 16, and they are long fixed by now. So the first one, the namespace limit, that was a very nasty one for us. So in the earlier versions of Aerospike, you could only have like 4.2 billion objects per namespace. And if you exceeded this number, your node would just crash. We are using relatively big machines, so we didn't just want to use like 20% of the server because we have very, very small objects. So we worked around that by using 10 namespaces per server. Before we even touch Aerospike, we hash the access key to pick one of 10 namespaces. We still do that before every read and write operation up until today. This allowed us to store 42 billion objects instead of 4.2 billion objects. Then the next one with the migration. In the very beginning of our Aerospike usage, the default amount of parallel migrations was very high, was something around 128 or 256. And each migration also needed quite a lot of memory back then. And because of that, we actually once ran into an issue where we wanted to add a new node, which was meant to prevent running out of memory. And this actually caused a situation where we ran out of memory. Nowadays, the migrations need a lot less RAM, and also the default values are a lot smaller. I believe it's 4 or something like this. So this is not an issue anymore. Then the data distribution, and by this I mean the distribution of data across all the nodes of the cluster. What we noticed is that some of the servers use like 20% of the disk, while others use 50% of the disk. And this resulted in a very uneven use of storage and of IOPS. Now, this is also solved nowadays by a feature that's called uniform balance. But back then, we worked around that by running a simulation on data distributions across the buckets before we added a new node. So Aerospike decided where to put the data based on the node name, and we brute forced names until we found a new name that allowed us to have a good distribution of all data across all the nodes. But again, like you don't need to do this nowadays anymore because there's a feature for that. And then secondary indexes, yeah, let's just pretend they don't exist. So we then continued to use and learn Aerospike, and relatively soon after we stopped using the community edition, we migrated to the enterprise edition. So we started using XDR. It does now all the data syncs between our data centers. We also used Aerospike for other use cases. For example, our tracker store. It's very important that we only use the latest version of a record. So that's why we use it there. NVMe all flash, this is a very big one for us. This is actually a feature we requested where we collaborated with Aerospike during the development. So the big change here is that the data is not longer stored in memory, but on NVMe drives. And this allows us to not only reduce the amount of memory in our servers, but also allowed us to store up to 4 times more data per server than before. And this again resulted in a great cost reduction. Same for server-side compression. Like we see that we can store a lot more data because we see a compression ratio of 0.6. And as you can see, we are still pushing Aerospike to its limit up until today, and we are still collaborating with Aerospike and improving their product as much as possible. So today we have like over 3 million read transactions and over 2.5 million write transactions per second. We also have lots of data in it, and we are nowadays in more than 1 location. We are using 3 locations. As I said, we are using XDR for that. And again, I cannot imagine doing any of this with our Redis approach. If we would be using Redis today, we would need around 1,600 servers, and I have no idea how we would scale that across 3 data centers. So this actually concludes our story of our central store that we use here at Adjust. So please let me know if you have any questions.
Well, thank you, Robert. On behalf of Aerospike Marketing, I'll be taking over for Ken to do the Q&A, if that's okay with you.
Yep, sure.
Yeah, so again, I really enjoy this presentation for a couple of reasons. Just kind of hearing the story or the history really about Adjust and the fact that you are one of our longest, most tenured, in a way, most demanding customers. So I guess thank you for being working with Aerospike and partnering with us. So thank you for that. I wasn't sure if you said early on that you manage overall, whether it's not just with Aerospike, but 1,000 servers. Is that right?
Yes, our fleet is around 1,000 servers.
And so I wonder if you could tell the audience or tell us a little bit about the DevOps tooling that you're using and any that you also use to manage Aerospike.
There's actually nothing really special there. We push our precompiled images to the servers when we finished our provisioning process, and afterwards it's just managing the servers via Rex. And Rex is similar to Ansible, basically. And we have written our own, we call it recipes for that, and it's really just normal DevOps work.
Well, I guess normal is good. Normal means no urgency. Early on, you said that you deployed on bare metal, and I was wondering if you had any advice about, when to use the cloud for Aerospike and when to use bare metal, and what factors should architects maybe consider?
Yeah, when it comes to cloud and bare metal, that's almost like a religious question. I think there's no one size fits all answer. In our case, we have a very high base load. Load never goes down, so you really cannot benefit from the advantages of cloud setups, which in my opinion is that you can turn stuff off when you're off peak and bring it back on when you're peak. And when you have really big peaks, then you can just deploy as much as you need. Our load is relatively steady, and that's why we decided to go with bare metal hoster, LeaseWeb in this case. And there's no fluctuation. So that's why we can actually benefit from a very good cost to what you get ratio. So basically we have a very high bang for our buck. And but this is something that everyone needs to check individually. But we of course also use cloud setups at Adjust, like we use it for CI/CD staging, pre-production setups, where it makes sense. And there we also deploy Aerospike in the cloud, basically.
Yeah, I mean, I think given your, I'll say, relatively large size, it's almost like if one part of your business goes down, another can go up. It just averages out. So ergo, part of the stability, I might guess. Talking about cloud a little bit, I don't know, or maybe even on-prem, but Kubernetes seems to be very hot with containerization. Does this play in at all? Does it have a place in Adjust? Does it have a place with Adjust with Aerospike?
We are actually currently evaluating Kubernetes very heavily, not necessarily for our attribution stack, which is very, very high traffic, but for pre-production or staging environments, it's very interesting to just be able to push out complete environments with low effort and basically test from scratch. And also for smaller deployments, if we want to do like data residency or locality of data, where it doesn't make sense to have a complete bare metal server setup, there we would also go with Kubernetes and deploy also Aerospike within that. Well,
I would hope maybe you would use our relatively new Kubernetes operators. Okay, could you tell a little bit about any analytics tooling that you might be using in conjunction with Aerospike? Just out of curiosity.
Sorry, we use Aerospike really just like a traditional database, a very fast database, if I may add that. But we are not using Aerospike in conjunction with analytics tools per se.
Okay. In terms, it's hard to say because you guys have, again, been on the cutting edge. Your last slide listed it out, XDR, strong consistency. You're now all flash, you're using compression. And you're a company that's experienced really hyperscale growth. And this might be our last question really is, what do you think about the next 5 years? What does it hold for you? What sort of growth do you expect? And then also, what are some of the things you might look for from Aerospike to help support that growth?
So, I mean, we grow with our customers, and the industry has been growing more or less exponential in the last decade, and I expect it to continue. So we hope that Aerospike scales with us. So far, I have no reason to believe that's not the case. And I think, yeah, when it comes to new stuff from Aerospike, I think we will be able to heavily benefit from these filtering and XDR, for example. And there are a lot of other things that we are looking forward to start using. Just yesterday got the mail from Srini with the updates. Yeah, we are basically we will scale Aerospike even further.
Okay, well, I think with that we'll end. Again, on behalf of Ken, myself, the rest of Aerospike, thanks again for participating in Summit this year, and again for your continued partnership with us. So thank you.
You're very welcome.
All right, thanks everyone.
Thank you.